Right. Where are we at? Bam, bam. Okay. What the hell is that? Right. Who's here? Let's get this show on the road. Cool. Right. So this sounds like a 2012 Minecraft Let's Play. Well, I mean, it's going to be way more interesting than a 2012 Minecraft Let's Play. Okay, cool. So, who's here? I can see I've got Alex, I've got Farrell. Anyone else lurking there? Want to make themselves aware of what's make themselves aware? That doesn't make any sense, does it? Make themselves known. Make me aware that you're there. There we go. It's Sunday night. Yesterday I went to London and I saw King Tutankhamun, which was nice. But today is Sunday, and rather than seeing King Tutankhamun, what I'm going to do is I'm going to go over some computer science stuff. Now, I did say 6 o'clock. It's Wednesday. I should probably end the stream. I did say 6 o'clock, so I will. It's currently 5:57. I'll give people a little while to sort of like trickle in. But if you guys have got any specific areas that you want me to go over, then I can form some sort of plan and I can write them down in my little text box here. See that text box? Yes. You may have noticed as well. I have a new telescope. It's rather large. When I say rather large, I mean it's preposterously huge. So there you go, new telescope. That's kind of cool. I've messed up my camera now. Cool. Okay, so do you want to see the list of topics? Where's the list of topics? This is obviously the OCR GCSE Computer Science spec. Here is a list of all of the topics from both sections, Component 1 and Component 2. We've got systems architecture, we've got memory, we've got storage, wired and wireless networks. We have network topologies, protocols and layers, system security, system software, ethical, legal, cultural and environmental concerns. We've got algorithms, we've got programming techniques, we've got producing producing robust programs, computational logic, translators and facilities of languages, and data representation. Now, the more astute among you may have realised that there's only one mock exam on your timetable, whereas there are two actual exams. What I've done is I have amalgamated two exams into one. So 40, there's a total of 80 marks. 40 of those marks will be from Paper 1 content and 40 of them are from Paper 2 content. What does robust programming mean? That is things like adding verification and validation to your programs to ensure that they do not break. It is writing your programs in such a way that they are easy to maintain, and it is also things like adding or anticipating runtime errors that may occur and adapting your programs so that said runtime errors do not occur. That's what producing robust programs means. key. Just going to sort something out here. Move that over there. What have we got here? Boom, that can go into there, we hope. Yes, that's good. I can actually see what's going on. I can see I've got 3 concurrent viewers. Right. I actually just realised that music has gone. Yes, that was my sort of play the music while we wait for people to arrive. I'd like to go over TCP IP structure. Right. In which case I will write TCP IP structure in the box there. Any other topics you want me to go over? Obviously, TCP IP structure, that falls under the purview of network topologies, protocols, and layers. Binary stuff. Okay, I will put in binary stuff. Binary stud? No, binary stuff there. I don't know what a binary stud is. Okay, so we've got TCP IP structure, binary stuff, any other areas. It's my hope that you won't want me to go over ethical, legal, cultural, and environmental concerns in any great detail. Perhaps I mean, any of these units probably don't have time to go over in a massive amount of detail. But I can sort of answer questions that you have. Are we allowed calculators in the exam? No, you are not allowed calculators in the exam. Which means conversion to hexadecimal, you will need to either be able to divide by 16 or use my patented technique of dividing by 2 4 times in order to find the original value. Logic too. Okay, I'll whack logic in there. Cool. Any other areas you want me to go over? I figure if we sort of gather a plan of action for the first, say, 10 minutes or so, then we can spend the rest of the time going through this stuff. Okay, layers. You mean network layers, I assume. I will put network layers tack that onto the end of TCP/IP structure there. Okay. Because TCP/IP structure and network layers, it falls under the same thing. System security and systems architecture. Okay, system security, and system. It's kind of weird typing stuff and seeing it appear. Anyway, system architecture, any particular areas of that, or what do you want to know? Huh? What do you want to know? CPU. Anything particular about the CPU? Or because I mean, the systems architecture is pretty much all about the CPU and the cache, I suppose, and how the CPU accesses memory and whatnot. For architecture, I was thinking, yeah, fetch, decode, execute cycle. Cool. Okay, we will do all that. When we look at the fetch, decode, execute cycle, we shall also investigate the way that the von Neumann architecture is structured. Yes, that's right, von Neumann. The way you spell it is like this: von Neumann, like that. It means Newman in German. You didn't know that, did you? Okay. So 5 more minutes to wait for the peoples to arrive, and then they can. I mean, we've got a fair amount of stuff to go along. I can't remember who. I think it was Alex asked about binary stuff. Any particular part of binary stuff? You want to go over the whole lot, or what is the deal there? Do you want denary to binary, binary to denary, denary to hexadecimal, hexadecimal to denary? Don't insult your German skills. Why? Wouldn't conscience the thought. Bits you think will trip people up. I mean, anything has the potential to trip you up if you do not read the question properly. That's my advice for you. Read the question through thoroughly. Read the question through twice, and maybe highlight certain sections of the question before you start answering. And also, make sure you read through the entire paper before you start answering the questions, because you can earmark the questions that you want, that you are more, confident with first. But I'll tell you what, down the bottom here, if I put exam technique here, is that fair? Exam technique. We can go over a bit of that near the end. It seems I've got seven concurrent viewers here. I can only see a few people actually in the chat though, so feel free to chirp up. I mean, you can carry on lurking if you want to. I do not mind. But obviously, if I know you are there, then I can help you out and answer your questions for you. So if we say 3 more minutes to get some sort of action plan in place, and then we'll crack on with this stuff. So first thing that we're going to cover is TCP/IP structure. So I should probably find my resources on that. That's GCSE Computer Science resources, Year 10 networks, network topologies, protocols, and layers. Let's go whack that down there. Boom, there it is. I'll just quickly skip back to the thing. Quite like to run over the symbols for logic gates. Yep, okay, cool. We will symbols and stuff like that. There we go, symbols and stuff. Things to bear in mind with the logic gates, although I taught you a vast variety of logic gates, the only 3 that you actually need for the exam are AND, OR, and NOT. And the main reason for that is that all of the other logic gates can be built out of those 3 gates. So you're not late, George. All we've been doing is I haven't actually kicked off yet. I was waiting for people to arrive. What we've been doing is discussing what areas you'd like me to go over. So if there's any particular areas you want me to cover, in my over here you can see my list of things that I am currently planning on covering. If there's anything I don't need an excuse as to why you're late. That's fine. We're going to start in about a minute. Alright, so about 1 minute. So if there's any additional things that you want me to go over, let me know now so I can add them to my list. What did I say? TCP/IP, binary stuff, logic, systems, security, packet switching. Okay. I will cover packet switching when we do the TCP/IP structure. The level of understanding that you need for packet switching is pretty much limited to the network layers. You don't need to know the difference between packet switching and circuit switching. You just need to know basically what packet switching entails. So as far as I can tell, at the moment I have Alex, Farrell, Joey, George, Harrison, Joey, and unnamed cyber warrior number 4. Right. Okay, it is currently 10 past 6. I had originally planned to do an hour on this, but you know how these things go. I'll probably end up doing a little bit more than that. We shall see. Okay, so just to let you know how I've got my screen set up here. I have the I can see the same thing that you can see on the screen here. I also have the YouTube chat up down here, so I can see that. Bear in mind there is a slight delay between the time that you type in a message and the time that I will be able to see it and respond to it. Maybe about 10-second delay. Okay, so I'm not ignoring you. That it is what it is. Okay, so here's the plan. We're going to have a look at networking. We'll look at the TCP/IP structure. That covers Google services. Yuck. Well, yeah, okay, Google services. Yuck. But you know what, Alex? At least they are not complicit in an illegal annexation of a foreign nation like Apple are. So we'll have a look at TCP/IP structure. We'll look at packet switching. We will look at network layers. We will then look at binary stuff. We will look at, I mean, let me just qualify that. I in no way am saying that Google is a good company. All big corporations are bad. Bear that in mind at all times. We'll look at binary stuff. I don't know what you want specifically to cover with binary. We will look. Well, we'll have a blitz through all of the binary stuff. Do you want me to go over how images and sound are stored? We can do that. Or if you just want me to do the conversions, we can do that. But you can tell me that when we get to that bit. Insertion sort. Right. Okay. I'll stick this down here. Insertion sort. I'll stick that down there. If they're on the exam, well, the thing is, here's the thing, Alex. I can't tell you what's on the exam because even though I built the damn thing, a part of the joy of being a student going to an exam is you never really know what to expect. And so what you need to be able to do is understand all of this stuff that is on here. Okay, so I'm not going to tell you what's on there. I'm not going to tell you what's not on there. There is the possibility for literally all of this stuff to appear. Who knows? Maybe it will, maybe it won't. Okay, but you need to be able to understand it, or at least pretend that you can understand it in a convincing way. We will look at logic. From what I can tell, the logic stuff, you just want to know the the symbols. So we'll go through that. System security, not entirely sure what you want to know about system security, but we can have a quick blast through that stuff. Systems architecture, we'll go over the fetch, decode, execute cycle. We'll look at the various registers and the structure of the von Neumann architecture. And then we will have a look at the insertion sort. And then at the end, I'll give you some techniques that will help you out in the exam. Number one technique, don't panic. That's there it is. Okay, I've said it. Yeah, I mean it's important, but it's not the real thing. So if you mess it up, it doesn't. I mean, it kind of matters, but it doesn't. You know, don't stress about it. Basically, is what I'm saying. Do your best, but if you totally fluff it up, we can work on it. We can fix things. Okay. No point panicking about anything. Never worth it. Never worth it. You always perform worse if you are stressed out. Different types of cipher. Yeah. Okay. We'll have a brief look at the Caesar cipher and whatnot in the system security section. Okay. I'll put ciphers in there. Okay. Cool. So we've got a list of things that we're going to do. Let's get crack-a-lackin'. Global warming is in my house. I mean, global warming is happening. It's global because it's everywhere. You can't. There is no escaping it. It is happening. All you can do is hope that government policy changes across the board. Let's get started. Right, binary. Let's do some binary, yeah? First of all, I mean, stop me if I'm going too fast or too slow, or if you know this stuff. But binary, I shouldn't really have to go over binary to Denry conversions, right? You should know what these magic numbers are already. 1, 2, 4, 8, 16, 32, and so on and so forth, all the way up. If you're ever in any doubt what these numbers are, top tip, start off on the right hand side and write the number 1, and then double each time. 1 times 2 is 2, 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, 16 times 2 is 32, 32 times 2 is 64, 64 times 2 is 128. Now you do not need to go any higher than 128, but if you did, you'd go 256, 512, 1024, 2048, 4096, 8192, 16384, 32768, 65536, and so on and so forth. But you don't need to. 128 is all you need. Okay? So do you just out of interest, do I really need to go through binary to Denry conversion here? Do I need to go through binary to Denry conversion? I've got 2 votes for no. No. Got 3 votes for no. 4 votes for no. There's 7 people. I mean, no belittling of people, please. Right, okay, so I'm not going to bother with binary to Denry because you guys obviously know binary to Denry. What's next on the list here? Denry to binary. Do you want me to go over Denry to binary? I've got to vote for no. I've got a. What is that symbol? Is that a yes? You want me to go over Denry to binary? Wait, no. Is this? No. No. Right. Remember that bit when I said what stuff about binary do you want me to go over? Quickly go over Denry to binary. Okay, brilliant. Right, let's do this. So here's the thing, right? Binary to Denry. There's a few things that you need to know, right? First of all, you need to know what the number is that you're converting. Now, in this example here, I've actually only used 7 bits. I'm going to fix that. I'm going to add something on to the insert column to the left. I'm going to add a column here, 128. Okay, I'm going to start off here, right? So, the way that it works, you've got a number that you are converting. You, in the exam, will always be converting using 8 bits. Okay, this is the way that it works. You start off with a number. In this example, we are converting 73. Right, I'm going to note that down here. Here's my 73. Right. Yes, assume that you're using 8 bits unless told otherwise, all right? So 73, I compare it to the first. I'm starting from the left-hand side, I'm working my way across, right? So I compare the number that I'm converting, which is 73, I'm comparing that to 128, right? 73 is less than 128. There are no 128s into 73, it's not possible. So I can put a 0 down here. Right? Because there are no 128s in 73, I put a 0 underneath it, and then I move on to the next number. Now, we're in a situation where we've got 73. 73 is actually more than 64. We can fit a 64 into 73. In that case, I put a 1 in the column underneath it. Okay. Now, after I've done that, I have to subtract 64 from my original 73. And you know what? I'm going to put it like that. So it's easier to see, right? So I'm going to subtract 64 from 73, and I am left with 9, right? I don't know why I put 09 in there. There we go. I'm left with 9, right? 73 minus 64 is 9. 9 now becomes the new number that I am looking at, right? I don't need to worry about 73 anymore. That's done. We gave 64 of our 73 over to this column here. I'm pointing at the screen and you can't see me, so I'll wiggle the mouse around. So we're carrying on with 9 as the number that we're converting. 9 is less than 32. We can't fit any 32s into 9, so we put a 0 in there. We can't fit any 16s into 9, so we put a 0 in there. But now we're at a situation where we have an 8. 8 is less than 9, which means we can fit 1 8 into 9. So I'm going to put 1 down there. I'm now going to subtract 8 from 9, and I get the answer 1. Okay? 1 is now the number that I am looking at. Okay? So 1 is less than 4. I can't fit any 4s into 1. 1 is also less than 2. I can't fit any 2s into 1. Right? Why is that not typed? There we go. 1 is equal to 1. I can fit 1 1 into 1. That was a silly line, wasn't it? Okay, so what I do, I put a 1 there, and then I'm going to go and subtract this 1. And the reason I'm doing that is for checking purposes. Okay? If I subtract 1 from 1, I end up with 0. I have now reached the end of my binary number that I've converted, and the number that I'm trying to convert is a 0. If you get to the end of here and you do not have a 0, if you have something more than 0, you know you've messed up somewhere. Okay? Now, if you ever get to the point, like if I was doing 72, for instance, if I was doing 72, we'd get to this point here where we subtracted, if I did 72 minus 64, we'd end up with 8 there, right? I do 8 minus 8, I get 0. I'm not at the end yet, and I'm on 0. If that ever happens, you can just fill all of these with 0. Okay? Does that make sense, how that works? Yes, good. That was mostly aimed at Alex. He was the one that asked me to quickly go over it. Makes sense, nothing new. Good. It says here, do we state it's an overflow error or write the 9-digit binary and then state overflow? You write the 8-bit binary without the overflowing digit and then write overflow next to it. So you will have 8 bits, right? You write out those 8 bits as the answer and then you write overflow next to it. Okay, you don't write 9 bits, you discard the overflowing 1 and you write overflow next to your 8 bits of numbers. Okay, wicked! Right, so I'm just going to... oh, didn't mean to do that. There's the binary. What about hexadecimal? Do you want me to do binary to hexadecimal? Hexadecimal to binary? What do you want me to do in terms of hex? Denry to hexadecimal? Hexadecimal to denary? Those seem to be the ones that most people struggle with. Binary to hex skip. Yeah, okay, that's fair enough because that's super simple. So you want me to do denary to hexadecimal, hexadecimal to denary, yeah? Hex is always confusing. Okay, cool. Well, we'll go over hexadecimal. Okay. But the thing to remember with hexadecimal is that it is base 16. If you remember that it's base 16, I say you can't go wrong, but it becomes less easy to go wrong. Okay, so hex to denary, I think is all in this one here. That's binary to hex. Hex to denary, is that what we just said? Hex to denary. James, I have your maker phone. Do you want me to give it to your sister and she can take it home to you? Okay, cool. I shall organise that. Right, okay, hex to denary then, yeah? We start off with a hexadecimal number. We're going to use F3 as our hexadecimal number, right? The way that this works is you split it into 2 digits still, just as if you were converting to binary. But the thing you've got to remember, right, because it's base 16, look at the columns. On the far right, we have a 1, just like everything else. But instead of going up by 2 each time, like you would do with binary, you are going up by 16 each time. Now that does map perfectly onto the binary columns, because you're taking every 4th column. But all you need to remember is that you have a 16 here, right? We are going to convert F3. That's our number. Here it is, F3 down the bottom here. Okay? Now with F3... there's 2 things that you need to do, right? And everyone always forgets the first one. And when I say I mean everyone that gets it wrong will forget the first one. Okay, we are taking that first digit. That first digit is F. What is F as a denary number? Yes, F equals 15. Right? F is 15. Right? What we have to do is multiply this by this number at the top. Right? You don't have to do that in binary because you always got 1s or 0s, and 1 times a number is the number and 0 times the number is 0. But with hexadecimal you have to multiply by this number. So we've got F is 15. So we have to first do 15 times 16. And 15 times 16 is what? $240, correct. Right? But we're not done yet because that just gives us this first column. Right? We still have to do something with this column. And it's super simple. In theory, all you're doing is multiplying this number by the number on top, but it's a 1 on top, so you don't actually have to do anything with it. You just add it on. Okay, so we've got 240. 240 plus 3 equals 243. Okay, that's it. You multiply the first digit by 16. You multiply the second digit by 1 and add it on. Yeah? So it's this times 16 plus that. That's all there is to it. You know? 2 steps. That times 16 plus that. That times 16 plus that. That times 16 plus that. Okay? I mean, you can practice this just by writing 2-digit hex. You know, you're only ever going to be dealing with 2 digits of hex. Simple, right? So that's hex to denary. Now denary to hex, that's the one where everyone's like, oh god, 16 times tables, don't know my 16 times table, blah, 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 blah. So some techniques that you can use. You can either write out the whole of the 16 times table at the side of your exam paper, or there's a better way of doing it. All right? Here is the easy way of converting denary to hexadecimal. Because the way that you're supposed to do it is you take the number. So in this example here, we are converting 77. What does hex go up to? 1, 2, 3, 4, 5, 6, 7, 8. Well, it's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. A, B, C, D, E, F. F is the highest, 15. It can't go beyond that because 16 in hexadecimal is 10. Okay, so we are going to convert 77 here. Ordinarily, what you would do is you would do 77 divided by 16. Okay, now if I said to you, what's 77 divided by 16? You can't use a calculator. You'd probably sit there going, oh man, well, how am I going to work this one out, right? But if I said to you, what's 77 divided by 2? You could probably do that. I mean, yeah, it's an odd number, but you could do 76 divided by 2, right? And if you know that, then you know what 77 divided by 2 is, because it's just the same thing, remainder 1. Okay, so what is 77 divided by 2? What is 77 divided by 2? It is 38, remainder 1. Okay? 38, remainder 1. Hang on a minute, I just need to format paint this. Okay? 38, remainder 1. This is what we're going to be doing. Okay? So we are dividing this number by this number. You know what? I'm going to change the colour here. I'm going to change that colour to cyan. Like that. And... oh, did I not just change that to cyan? I messed up. Because I changed the line number, not its text color. There we go. I'm going to change that to cyan. I'm going to change this one to yellow, just so that we can see the difference here. Right? 77 divided by 2 is 38, remainder 1. Okay? We're not bothering with decimal points, doesn't matter. We're just interested in the remainder. The remainder is either going to be 0 or it's going to be 1. If your number is even, your remainder is going to be 0. If your number is odd, your remainder is going to be 1. So all you have to do is halve it and write either 1 or 0 in there. So let's do it again. 38 divided by 2 is what? (19), remainder 1. Do we agree? Yeah, that's more like it. Not remainder 1, remainder 0. It's an even number, so there is no remainder. Okay? Next up, we've got 19 divided by 2. What's 19 divided by 2? (19 divided by 2) is 9, remainder 1. Okay, we're almost here. Almost there. Right, and now we have 9 remainder... 9 remainder 1. So 9 divided by 2 is what? (9 divided by 2 is 4, remainder 1. Okay? So now we've filled out this little table. We've divided 77 by 2 4 times. If you divide a number by 2 4 times, that is the same as dividing it by 16. So 77 divided by 16 is 4, which means our first digit is 4. Okay, the first hex digit. When converting 77 denary into hexadecimal, the first digit is 4. Okay, let's go to the next slide here, where I've already filled it out here. This number here is the first hex digit. The remainders that you left as you were going through it form a binary number. Convert that binary number, and you get your second hex digit. Okay, so the first hex digit is 4. Right? The second hex digit is equivalent to 1101 converted to denary, which is 8 plus 4 plus 1, which is 8 plus 4 plus 1. Is 13. What is the hex digit for 13? C. Okay, A is 10, B is 11, C is 12, D is 13. Right, here's a top tip for you. Right, when you are creating or when you are converting hexadecimal numbers, right, do this. 10 equals A, 11 equals B, 12 equals C. Write all this stuff down next to whatever question you are being asked. 14 equals E, 15 equals F. Right? If you write that down, then you can easily refer to it. Okay? Now, because we've got this number here, that equates to D. we've already got this first digit, that's just 4. We've converted that. Our conversion is now 4D. Okay, that is our final answer. Right? Do we get that? Now, there's nothing stopping you if you can divide by 16 and then find out what the remainder is when you've divided by 16. There's nothing stopping you doing that. Right? I think that this method is easier to do because you're only ever dividing by 2 and then doing a simple binary conversion. Okay? And they're both valid. Both get you the correct answer. Okay? Thing to remember, it's got to be 4 times that you do it. Yeah? Got to be 4 times. Okay. And that's pretty much all the binary conversion stuff that we need to do. So how about we do some TCP/IP stuff and some networky networks, and then we'll see where we're at. Sound good? My computer is very loud. I mean, you mean the sound coming out of it is loud, or the fan is loud, or which part of it is loud? Put a plug in it. Okay. Cool. Right. Okay. I will let you deal with loud computers. Here we go. Networks then. So you guys want to know about network layers, and you want to know about what was the other thing? Network layers. Oh, packet switching. Okay. Did you want to know about network protocols? I'm assuming you know what a protocol is. Just in case, a protocol is a set of rules which explain how to do something. TCP and IP are both network protocols. Do you know what TCP stands for? Do you know what IP stands for? If you do, then say. If you do not, then say, I do not know. I don't care about meme. Transmission control protocol is correct, although as you are not taking the mock exam on Tuesday, James, I'm kind of more interested in what other people have to say there. Yes, transmission control protocol, internet protocol, and they usually go hand in hand. Okay, they don't always go hand in hand, but in terms of transmitting information across the internet, the TCP and IP protocols go hand in hand, and they actually control 2 different parts of the layer stack. Okay, I mean, I don't mind you like chipping in, James. That's fine. I'm just saying that other people have more at stake here. Yeah, that's fine. Right, here we go. Protocols, star networks, mesh networks, hybrid networks, the TCP/IP layer model. Boom! Right, so here's the thing that you need to understand. Right, when you send information across a network, it does not just send the whole lot all at once. Right, it splits it up into packets. Who can tell me what a packet of information is? Okay, I tell you what, write me a decent definition of what a packet of information is, yeah, and while you're doing that, I'm going to go and make myself a cup of coffee, and then by the time I get back, I'll be able to review it. Okay, so just explain to me what a packet is, and while you're doing that, you can listen to this. Right, cool. I'm probably going to get hit by a copyright claim or something now. Give me a second. Obviously, the phone is not actually ringing. That's a thing. Blah, 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 blah. Where are we at? Something went wrong. Here we go, we're back! We are back! Right, let's have a look and see what you guys said about packets. A small amount of data with a header, a checksum number, and the payload that can be easily sent across the network. Yes, that is correct. What is the checksum number? Can you explain to me what the checksum number is? You don't need to specifically know about checksum numbers, by the way, but you do need to know what a check digit is. So if you can explain that to me, that would be cool. Chunks of information which are sealed in virtual envelopes sent from the computer containing an address to the server and computer about the request. Yes, that is a pretty good explanation of what a packet is. There are no adverts on here, by the way. I'm not sponsored by anyone, nor would I ever be sponsored by anyone. So there's a thing. Hall of the Mountain King. What's happening exactly? Yes. Small amount of data sent individually between computers on a network, part of a larger piece of information. Multiple are sent so the first arrived can be used. Well, I mean, they all need to arrive before they can be used, but I see what you're getting at there, and that's a pretty good explanation. The digit represents the order that the data needs to go in. Not quite. That's not quite what a check digit does. I'll go over check digits in a sec for you. Checksum is a number calculated by both computers after transmission. Yeah, to validate the data. That's exactly what the checksum is. So basically, when you get all of the data, there will be this. The checksum is basically it's a maths. It's a maths that needs to happen, right? And so you receive this stuff, and then you do the maths. And once you've done the maths, if your maths matches the maths that have been sent, you know that it's all correct. But if your maths does not match the maths that's been sent, something's gone wrong, and you probably need to get your stuff retransmitted. We'll go over checksums in a little bit more detail in a sec. Okay, so a pretty good explanation of packets there. You all seem to understand the concept that if you've got a big page that you're sending across the internet, you can't send it all at once. You have to break it up into these small pieces of information. And the reason you have to do that is because when they get sent across the internet, they don't all follow the same path. They go all across round various different routes. They take whatever route seems the best for them at any given time, and then they are reassembled again. Reassembled at the other side. Okay, so you send a request. You say, "Can I have this file about I don't know what it is, whatever this text file containing ASCII artwork, please. And even something as small as a text file containing ASCII artwork has to be broken up into packets before it can be sent. You get tiny little bits of information, okay, and it's like pew 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 across the internet. Most of them will probably follow the same path, but then when the paths get clogged, they take different routes. Okay, it doesn't matter which route across the network these packets take, as long as they get to their destination. And once they've got back to their destination, there will be some instruction. Each packet contains an address that it's going to, an address where it's just come from, and it will contain some information about what order the packets need to be reassembled in. Okay. No, my gang sign is, wait, is that like that? West Midlands, yeah. So anyway, yeah, so you kind of get what packets are. Does that idea differ between mesh and star networks? No. If you are using a packet-switched network, it does not matter what the topology is. Your data is being sent as packets. Okay, the only time that it's different is if you are using a circuit-switched network rather than a packet-switched network, which is incredibly rare these days. Things like the old telephone network were circuit-switched networks. The idea is that you form a connection which exists for the duration of the transmission. It's almost like you've wired up these two things, and while you are using that connection, nothing else can use any of the components on that connection. Once the data transmission has been finished, the circuit is broken, and then new ones can be formed and stuff like that. You can probably guess why packet switching is favored over circuit switching, especially on the internet, for example. I want Telnet back. Telnet never went anywhere, George. Telnet's still here, but it's kind of insecure as hell, and no one really uses it. But you can set up your own Telnet server, you know. If you're sensible, though, you'll use SSH rather than Telnet. They want the fastest route. Well, the thing is, yeah, they want the fastest route, but they don't really know what the fastest route is necessarily going to be. The packets are fairly unaware. It's the routers at various nodes that send the packets around the network, and the routers can say, "Oh, you need to head in that general direction. It looks like that way is going to be the best for now," but the routers themselves don't have a big overview about like which the best routes are going to be. It's kind of like if you were using a sat nav, which rather than planning out your whole route for you, it made a decision every time you went to a junction. It said, "Oh, turn right here," and then you turn right, and then at the next one it's like, "Yeah, turn left." Okay, rather than planning it all out in advance, it just tells you what the most expedient route is going to be at each junction. A transatlantic slave. Okay, I mean, if you want to set up a Telnet server, it's super easy. By all means, do it, and I'll connect to it and show you why you should set up an SSH server rather than Telnet server. But anyway, so. Packets. Let's have a look at what actually happens when you click the button or when you type in a request, right? What happens is your request gets sent to a server, right? We're all on the level when it comes to client-server communication, right? You're accessing a web page, you are sending a request to a server, and the server is saying, "Ooh, do I have that page? Let me check. Yes, I have that page. Is this person allowed to have this page? If they are, I'm going to split the page up into packets. I'm going to send it out." Okay? So, yeah, I mean, like, if you want to find out how to set up a Telnet server, like, it's not like there's a shortage of information on the internet. Right? I'm not going to go into that now. Anyway, right. So, let's have a look at what actually happens. When the page gets sent back, let's have a look, right? There are 4 layers that you need to know about. Now, this is the TCP/IP layer model. That's what you need to know about at GCSE level. It is not the OSI layer model, which has 7 layers, 8 layers, depending on what you depending on whether you deem layer 8 a proper layer or not. Okay, so anyway, we start off with the application layer, right? The application layer, that's your web browser, if you like, right? The web browser is going to know how to handle HTTP data. It's going to know what to do with an HTTP request or with a page which has been served using HTTP. What does HTTP stand for and what's it used for? Tell me. It stands for sadness. It's not Hypertext Transmission Protocol, but semantically it means the same thing. Hypertext Transfer Protocol. Yeah, there we go. I mean, means the same thing, I guess, but yeah, HTTPS is so cooler. Yeah, that's true. And what does the S stand for on HTTPS? Secure, correct. And how is the security achieved? Encryption. Yes, it uses encryption. We'll get onto that when we look at system security. Finger wagging. Okay, so we've got our web browser, right? The web browser knows how to deal with HTTP, which means when the web server, which also knows how to deal with HTTP, sends this information out, it starts off, it gets the page, and it says, right, what does an HTTP response actually look like? I need to format this data so that it's actually looking the way that an HTTP response would look, so that when the web browser gets it on the other end, it knows how to handle that data. Okay, I'm obviously using web browser and web server as an example. It's the same with any client server system or any peer-to-peer system, right? Your application will know how the data needs to be structured before it sends it out. Okay, so once it's arranged that data in the way that it's expected to be arranged, it then passes that information off to the transport layer. Okay, so we've gone from HTTP now onto the transport layer. This is your TCP layer, right? This is where your big server response gets broken up into tons of different packets, right? Now, each protocol that you use to send stuff across the network will have different size packets. If you're using TCP, all the TCP packets will be the same size. If you're using a different protocol, then the packets will be sized accordingly. You don't need to know what the size of the packets are or anything like that. All you need to know is the transport layer takes the packets, takes the data and it splits it into packets. Okay? So it's broken it up into packets, right? And obviously there's information stored in those packets about how they can be reconstituted on the other end. Okay? Once the transport layer has done that, it then hands off each individual packet to the internet layer. Okay, so we started off with the application layer working on HTTP. Right? We then handed off to the transport layer. The transport layer was dealing with TCP/IP. It's converted those different packets and it's sent them to the internet layer. The internet layer uses IP. Okay? So what the IP protocol does is it stamps an address on each of those packets. It says this is the address where this stuff needs to go, but it also includes an address saying this is the address where this stuff has just come from. Okay, and that's important with some protocols because they will check to see whether the information has been received or not. And if it hasn't, it will send a request back saying, send that again. Okay, so once the internet layer has stamped an address on each of these, it then passes the packets to the link layer. Now the link layer is concerned with the actual physical hardware, right? So on the internet layer, this stuff will have an IP address. Whether that's IPv4, IPv6, doesn't matter, they will have an IP address. An IP address is not tied to a specific piece of hardware, right? You can assign IP addresses to different pieces of hardware. You can assign the same IP address to multiple different bits of hardware, which can cause confusion. But if you've got things set up properly, we avoid that. Now, the link layer, this is where the actual physical hardware is connected together using a MAC address. Now, a MAC address is essentially the same sort of deal as an IP address, but it is tied to physical hardware. Okay? Your network card will have its own MAC address, which will not change. Which means if you get banned from a video game by your IP address, you can reassign a new IP address, okay, and then you can get back into the game. But if you are banned by MAC address, you'll have to replace your hardware to get back in there. Okay? So it's effectively, yes, it's like the transmitter. Okay, so this is your network card, which is taking the packets of binary data and converting them into electronic information like pulses of electricity or pulses of light if it's sending them across a fiber network. Okay, and it's saying send them to this MAC address. Okay, it's joining together two MAC addresses. Now that's not going to be the final destination MAC address. Okay, it's going to be the next bit on its journey, if you like, right? So once it has connected the physical hardware together, it transmits that information, okay, and it goes across the network. Can't you replace the MAC address? No, you can't. You can spoof a MAC address. You might be able to flash firmware to change the MAC address, but I'm not sure about that. Generally, I mean, as far as you guys need to know, the MAC address is permanently tied to hardware. I mean, that's what the GCSE spec is expecting you to know. Okay, so yeah, you can change your hardware to get a new MAC address. Right. So once the data has been sent across the internet to its destination, all of this process happens in reverse. All of the physical packets, the data, the electricity, if you like, is received by the link layer, and it takes that information and it converts it back into the binary data that the computer understands, and it pushes it up the stack to the internet layer. Right? Now, the internet layer, what that can do is it removes that extra information about the address. It's like, okay, cool, this has just come from this address. It's checking, this is my address. It's definitely meant for me, right? Now, what it might do is it might send a message back saying, I just received this packet. Okay, not all protocols do that, right? But if we're talking about TCP/IP, it will do that, right? Once it's removed that extra information, it's kind of like it's unwrapped one layer of its envelope. It pushes it up to the transport layer. What the transport layer does is it reconstitutes all of those packets. Remember, each of the TCP packets has the information that it needs to be joined back together again. Okay, so the transport layer takes all of those packets, joins them all back together, and then it passes them up to the application layer. At which point the application layer looks at it and says, oh cool, this is HTTP data, brilliant, it looks like an HTTP response, what is that? Oh wicked, it's a web page, I'm going to display this in my browser. Okay? What does it do if it gets the wrong packet? It discards it. Okay. So that's basically the TCP/IP layer model, right? Your application organizes the data the way that it's supposed to be. It then passes that to the transport layer. The transport layer pulverizes it into these little packets and includes little bits of information saying how the things get joined back together. It then passes each individual packet down to the internet layer. The internet layer stamps an address on each of those packets and it hands it off to the link layer. The link layer converts them into whatever format is required for the hardware and sends them out across the network, right? When it is received, when that information is received by the link layer on the other end, what it does is it takes that raw energy, that raw light or electricity, converts it into binary data that a computer can understand, pushes it up to the internet layer. The internet layer removes the IP address information and then passes it up to the transport layer. The transport layer takes all of these packets and it reassembles them. Okay. Now, you might have heard the phrase TTL or time to. What does TTL stand for? Time to loss. TTL. What does TTL stand for? Time to live. That's it. Time to live. Wow. How do you forget that? So time to live. Basically, if the time to live expires, it will send a new version, right? And once it's reconstituted all, it passes it up to the application layer. The application layer does the reading of the stuff. Okay, so this is what's called a protocol stack because multiple different protocols are used. Okay, do you guys understand? Do you guys understand the benefits of using a layer model? Look, here's a little diagram showing how it passes down through the layers and then goes back up through the layers. Do you guys understand the benefits of using layers? Is there any other way to transmit data physically apart from binary? Yeah, you write on a piece of paper, stick it in an envelope, and put it in the mailbox. If you want to transmit data between computers, I mean, they read binary, right? So it's kind of got to be binary data. I'm just going to check my massages here. Checking the messages. Ow, yeah. Do 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 do. Right, anyway. Schoolboy response. No waste in other methods. Okay, right. Okay, so let's have a... Not entirely sure what this diagram was. Dunno. Okay, here we go. Why layers? If something goes wrong on one layer, the other layers are not affected. Okay? If there's some deal with your link layer hardware, you know, it's not transmitting for whatever reason, everything else is fine. All you have to do is whack a new NIC in there, and boom, it can crack on with it. It also means that you can upgrade different parts of your system without having to affect the other bits. If someone comes along with some amazing new technology, oh, check this out, man, we found a new way of routing packets around the network. That's cool. They changed that one bit. They can keep all the other bits the same. Okay? Different teams of people can work on different layers, which means that they can have specialisms in those different layers. If you totally understand like hardware programming, like you're a dab hand with assembly language or something like that, and you want to write hardware drivers, you ain't ever going to need to touch the application layer. Why would you? You can sort out the link layer. Right? If you're writing a web browser, you don't want to go through all the hassle of trying to understand how this data is actually sent across the network. All you want to do is say, okay, I've got an HTTP response, send it to the network thing, and then the other layers handle all of that stuff. Okay, I've put down here as well, if new hardware is developed, only the affected layer needs to be modified. The example, when fiber optic cables were developed. Okay, yeah, we need some new system to handle the link layer stuff, but we don't need to touch the rest of it. That works fine. You know? In the same way that if you imagine you're sending a letter to someone, the guy delivering it in his delivery truck, he doesn't need to know anything about you. He doesn't need to know what pen you used to write it or anything like that. He just needs to know where he's going. In fact, the guy driving the truck that delivers your parcels probably isn't even going to deliver it to your door. He's just delivering it between two different distribution centers. Okay? It doesn't need to know the rest of it. That's someone else's job. Same deal here. One way of remembering the layers. Learning is totally awesome. Yeah, link, internet, transport, application. Learning is totally awesome. There you go. Or you can remember the lady's name, Lita. I remember Lita because she was a female wrestler who I stole a whole bunch of moves from. But there you go. Are we good on TCP/IP structure and network layers now? We're kind of cool with that, yeah? Yep, cool. Right, I'm going to blitz that off. We've done most of the binary stuff. Did you want me to go over how images and sound are stored, or are you good on that front? We good? We good? I'm okay. Yes. Is that yes? You want me to go over it, or yes, you're okay? Bit of both. Right, okay. We'll do a quick whistle-stop tour on this front then, yeah? Bear with me un secondo. Basically, if you understand how character maps work, you'll understand like all of the imaging stuff, right? This is going to take a couple of minutes tops, right? So application of binary. Let's just go through this super duper whooper quick. You don't need me to go over character sets, right? Character sets are all good, yeah? That's the ASCII character set. Yeah? Each symbol in the ASCII character set is assigned a value. Your binary number tells you what value to display in your text, right? Simples. The way that graphics work is no different, except instead of looking up a symbol, you are looking up a color. Okay? Here we go. As an example, I have two colors in this incredibly high resolution image. I've got dark green and I've got light green. Okay, my dark green is mapped to the number 1. My light green is mapped to the number 0. 11011 means dark green, light green, dark green, dark green. Yeah? So if you've only got two colors, you only need 1 bit per pixel. Yeah? Which means each pixel is either 1 or it is 0. By stringing together all of the binary, you build up an image. Yeah? Here's another example. Look at this incredibly patriotic image right here. The difference here is that we now have 4 colors. Because we have 4 colors, we need 2 bits per pixel. Why 2 bits per pixel and not 4 bits per pixel? Yeah, there's 4 different combinations. If I had 8 bits per pixel, how many different colors could I have? I have a lot more than 4 colors if I had 8 bits per pixel. 8 bits per pixel. I've got 1 bit per pixel, it's 2 colours. 2 bits per pixel is 4 colours. 3 bits per pixel would be 8 colours. If I have 8 bits per pixel, it is not 16, it's considerably more than 16. I am disappointed. 8 bits. What is the highest number you can represent with 8 bits? Yeah, so highest number you can represent with 8 bits is 255. If we include 0, that means we've got 256 different colours. Okay? You've got to know this stuff. If it sounds like me banging on a brick wall, right, you've got to know this stuff. It should roll off the tongue. Yeah. Does the program that handled the data know the dimensions of the image and therefore where to start a new line, or is this stored with the binary? Most file formats will, at the start, they will have a little bit of information as to what type of file they are, whether a PNG or a JPEG or whatever. They will then have things like how many colors are in the image, and specifically what the color palette is if they use indexed color, and they will have the dimensions as well. So they will include that information in there so that they can be reconstructed. I mean, this is literally how raw pixel data is stored. You guys don't need to know the ins and outs of different file formats. Okay, but because we've got 2 bits per pixel here, each 2 bits refers to one of these colors. So you can see my first pixel is red. The color code for red is 00. The next pixel is white. The color code for white is 11. There it is. And so on and so forth. Blue is 01, so we've got a 01 and a 01. Okay? I don't think I need to explain any more than that. Is that cool in terms of images? You wanted to do sound, yeah? Cool. Obviously, just before we move on to sound, things to remember: the more bits per pixel, the higher the number of colors that can be represented. The more pixels you have, the higher the quality of the image. But obviously, as you increase the number of pixels, you increase the amount of data that you are storing, and therefore you can calculate the file size of, or you can estimate the file size of various images by working out how many pixels are in the image, how many colors are used, and therefore, or rather how many bits per pixel are used, and so on and so forth. So that means that GIF are 8-bit. Yes, they are. They are 8-bit indexed colored. They can display a maximum of 256 different colors. One of those colors can be transparent. But the way that GIFs are stored is the transparent color, it's still a color. Right, you might have loaded up a GIF before and found that it's got like really bright green or really bright pink in the color palette, and that will be the one that is flagged to be transparent. There you go. Cool. So there's images. Boom shakalaka. Let's do digital audio. Digital audio. Now, I'm not going to go through all this stuff about what sound is, but I am going to show you this thing. You will need to know what sampling frequency is. You will need to know what a sample is, and you will need to know what bit depth is. Oh, this reminds me. I set the sample rate of a WAV to the required for the Makerphone in Audacity, and it still won't work. Do you have any idea why? Not without seeing it for myself? No, I do not. So yeah, right. So the way that we store audio, it's kind of similar to the way that we store graphics, but it's a little bit more abstract. Okay. Here is a waveform. Any sound is made up of waves, right? They will have varieties of different frequencies, peaks and troughs, and so on and so forth. Okay. Well done for finishing your phone, by the way, George. Okay. So what we do is we take samples of the waveform at regular intervals. A sample is basically a measurement of the height of the wave at any given point. Okay, now you'll notice on my diagram here the samples are taken at regular intervals. Yeah, we've got 0, 1, 2, 3, 4, 5, 6, 7, 8, and so on and so forth, right? The sampling frequency is measured in hertz. If I have a sampling frequency of 400 hertz, how many samples am I taking per second? Hello, Will and Tiny, whoever you are. About 4. No, if my sampling rate is 400 hertz, how many samples am I taking per second? $400, correct. Okay, 1 hertz means once per second. If I'm sampling at 400 hertz, it means I'm taking 400 samples per second. Okay, now you don't need to know Shannon Nyquist theory, but in order to capture all of the frequencies in a wave, you need to sample at twice the maximum frequency in a wave. What you do need to know, however, is the higher your sampling frequency, the better the quality of your sound. Okay, so the way that it works, we take measurements of the waveform. We convert those measurements to binary. Those binary pieces of information are all stored together, and then we can use that information to reconstitute the waveform. Okay? Here's a more useful diagram here. You can see here I've got the measurements of the height of the wave above and below 0. Right. The way that we convert things to binary is we have to do something called quantization. Right. Quantization is necessary whenever we're converting anything to binary, which starts off as a continuous waveform or a continuous spectrum. Okay. So we cannot record precisely every single sample. What we have to do is we record the closest quantization level. So you can see here my first sample is at -4, my second sample is at 0, my third sample is at 4. Now my fourth sample, the actual waveform lies between 6 and 7. It's a little bit closer to the 7 than it is the 6, so we just say it's 7. Okay, there is no in between. Right? I don't know what this boopy bap bit bop nonsense is, but if it continues, there will be mutings. Okay? So here's the thing. Right? The more of these levels of quantization we have, the higher the quality. But just like with our images, if I just go back to our images, if I have 2 bits per pixel, I can only display 4 different colors. With audio, it's not bits per pixel, it's bits per sample. Okay? So I have got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 different layers of quantization here. If I've got 16 layers of quantization, how many bits per sample do I have in my waveform? I've got 16 layers of quantization. How many bits per sample do I have in my waveform? Only if you answer this question, FPT, whoever you may be. not 5. It's a good guess. It's close. Not 32. How many bits do I need to represent 16? I mean, you were close with 5. Remember, 0 counts as a value. 4 bits. Yes, 4 bits. We go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. We don't go all the way up to 16. As you can see here, we don't go all the way up to 7. But because 0 exists, right, that counts as a value. So 1 to 15 plus 0 gives us 16 different levels. Okay? Now, we can increase the accuracy of this. If I increase the number of levels of quantization, if I double them, I'll be able to get twice as much accuracy. All I have to do is add 1 bit. Okay? So here's an example. I have replaced my different values with zeros and ones. Okay? You can see I've got 4 bits. Right at the very bottom, my lowest value is 0, 0, 0, 0. Okay, and it goes all the way up to 1, 1, 1, 1. Yeah, it basically improves the sound quality. You can see here there are still these bits where the waveform goes in between two different levels of quantization. We have to snap it to the values that we have. If I added another bit, it wouldn't make the top go up any further. What it would do is add lines in between each of these. We'd double the levels of quantization, which means we'd be able to more accurately pinpoint this one here. We'd be able to more accurately pinpoint this one here, and we get a more accurate view of the waveform. Okay, so what you need to remember when it comes to digitizing audio is you take regular samples of the waveform, and remember, a sample is a measurement of the height of the wave. What you do with those measurements is you convert them to binary based on how many bits per sample you have, okay, and then you combine all of that binary together. Right? So here's some little facts about bit depth. Audio CDs, which are not really a thing anymore, but they are encoded using 16 bits. It gives a signal-to-noise ratio of 96 decibels, which is not quite good enough. CD quality is pretty good, but it's not as good as actually hearing stuff, because the dynamic range of the human ear is around 120 decibels. A bit depth of 20 bits gives a signal-to-noise ratio of around 120 decibels. So if we wanted to get like proper high-quality audio, we would sample at 20 bits. Why do you think we'd use 16 bits when we are using CDs rather than 20 bits? Limited storage space. Yeah, I mean that's the basic answer. If you're sampling at 20 bits, it's going to reduce the amount of time that you can have on your CDs. Generally speaking, a CD can hold enough data to give you I want to say 70 minutes of audio, and if we use 20 bits, it would be a lot less than that. Okay, so 16 bits it's one of those things where people have said, you know what, that's good enough. That's good enough. The thing that makes another big amount of difference is the sampling frequency. Okay, because CDs are sampled at 44.1 kilohertz, it means they will be able to capture frequencies of 22 kilohertz, and the highest frequency that the human ear can hear is around 20 kilohertz, which means they're pretty damn good in terms of the sampling frequency here. There's more to it than just that. You don't need to know that. Okay, things that you definitely need to know: the higher the sampling frequency, the higher the quality of the sound. The higher the bit depth, which is the number of bits per sample, the higher the quality of the sound. But of course, as those things go up, the storage requirements also go up. Okay, good. Any other questions on binary before we move on to logic, symbols, and stuff? Every guy I see, I always think to myself, did he pleasure himself today? It actually turns me on right there, and I don't know why. I mean, thanks for that, Annabelle. That's really useful insight, but I'm not entirely sure how that relates to computer science. So yeah, interesting. Interesting. Cool. So we're done with binary. We're ready to move on to logic, right? I'll take the resounding silence as a yes. Okay. Yeah, you only need to know 3 logic gates. That's why this is going to be incredibly quick. Let me pull up the stuff about logic. Logic, computational logic. Computational logic gates. Right, here we go. So, the logic gates that you need to know are this one here, which is a what is this one here? The one that I have clicked on right now. What is that? It is and. Yes, it is and. What else do we need to know? We also need to know this one right here. What kind of gate is that? It is an OR gate. Excellent. And the final one that you need to know is this one. It is a NOT gate. Okay. You do not need to know the XOR, the NOR, or the NAND gates. Okay. What you do need to know, though, you need to know how these things work, and you also need to know the symbols, which I believe are in my previous presentation. Just bear with me 1 second. Nope, they are in a worksheet here. Not that one. Right, here we go. Just whack this in here. There we go. So you need to know an AND gate, an OR gate, and a NOT gate. You also need to know these symbols. Okay. If I did something along the lines of this, I could do A and B, for instance. Okay, see how that works? I could also do B or C, and I could do, let's do something crazy, not E and F or G, for instance. Make sense? Okay. Now, Joey was the one that said, can you go over the symbols? I don't know whether you want me to go over the functionality of the gates as well, or you just want me to go over this. The guy who came up with this was like a V, an upside down V, and yeah. Things to the easy way of remembering this stuff is the symbol for AND kind of looks like an A without a cross on it. The symbol for OR looks like a V. The way that I remember that is like if you've got, I don't know, Chelsea v Spurs. It's either Chelsea or Spurs. Yeah, there's a thing, and you've got not. When do you use brackets? You use brackets when you want to ensure that something happens before something else does. So as an example, if I did something like this, if I did not not A and B, for instance, the way that this would work is I would do not A and B. But if I wanted to change it so that I have to do the A and B first and then do the not on the result of that, that's when I would use a bracket. So I'd do something like not A and B. Okay, in exactly the same way that you would use brackets in order to change the precedence of your maths, for instance. Yeah. Yes, just like in aths, George. That's right. So in order to change the precedence, that's when you use brackets. If you're ever in any doubt, there's nothing wrong with sticking brackets in there. Okay, if you want to make sure, right, I need to make sure that this is happening first. Yeah. Yep, no problem, FPT, whoever you may be. I hope this has been helpful for you. Is not A and B the same as B and not A? No, it is not the same. It's not the same. And I will explain to you here. Right, if you do B and not A, okay, that not happens first. You're doing not A and then you're ANDing it with B. Whereas here, you're doing A and B first and then applying the not. In fact, if you give me a sec, let's go to everyone's favorite logic site, Logically. What are you doing? Typed it in wrong. Let's go there. You're a NAND gate. Try Logically in your browser. Right, okay, so I can demonstrate right here. Let's say we've got, there's our A and there's our B, right? We've got our AND here, and we're going to need a NOT gate. There it is, right? And let's have an output there. Okay, so if I did not A and B, the way that it will work is like this. Here's A and B, and then that feeds into a NOT gate, and then that feeds into our output. You can see when I turn the first switch on, the output is on. When I turn the second switch on, the output is on. When they're both off, the output is on. When they're both on, the output is off. Right? If I was to do the same thing, but what was your second example? It was B and not A. The way that would work is like this. Here's not A. There we go. And then AND with B. There we go. And we get a light bulb in there. And you can see when they're both off, the output is off. When I turn one of them on, the output is still off. When I turn the other one on, the output is now on. And when I turn them both on, the output is off. So the actual it's slightly different. Does that make sense? My advice to you, if you are not sure on the functionality of logic gates, just go to Logically and play around with the stuff there. You only need AND or NOT, but you also do need to know how they combine together, for instance. All right. Is that cool for logic? Do you want me to go over any of the logic stuff, or? Is there any other logic stuff? I mean, not really. Cool. Right. Cool. So that's logic's done. What's next? So what's the time? It is currently 7:35. We've gone on way longer than I expected, but never mind. It's all good. So, right, out of the ones that are left on here, we've got System Security, System Architecture, von Neumann stuff, and Insertion Sort. Which of those would you like me to prioritize? Because I'm not sure whether we're going to have time to do all of them. So, let me know. Security. Okay, cool. So security. Okay, cool. Oh, it looks like everyone wants systems architecture rather than security. All right, give us a sec. Let's have a look, shall we?
Every morning I have the same problem. I have.
Right, good. Stop exist. What does that mean? Let me find the thing. So you want to know the... I'll tell you what, let's skip straight into the fetch, decode, execute cycle, right? Yeah, every morning I have the same problem. Fetch, decode, execute. Is this the one that I want? Is it the one I want? Ooh, ooh, ooh. Probably. Right, here we go. Right, here's my amazing little model of what the von Neumann architecture kind of looks like. But remember, this is an abstraction. This is not what it actually looks like. But it does include all of the registers that you need to be aware of. Okay, so we've got the PC. What does PC stand for? Program counter is correct. We've got MAR. What does MAR stand for? It's not Pringle counter. Pringle counter is not a thing. What does MAR stand for? Memory address register is correct. Okay, and we've got the MDR, which is what? The memory data register is correct. We've got the CIR. CIR? Current instruction register. Good. And the accumulator, which is often abbreviated to ACC. Right? Now, if you can't remember what all of this stuff stands for, don't panic. All right? You don't have to panic if you can't remember what this stuff stands for. But you do need to know what it actually does. Okay? You need to know the fetch, decode, execute cycle. You need to know how that works. Right? When you first turn on the computer, all of the registers are effectively empty. The PC is set to 0, everything else is empty. Okay? So, here's what happens. Now, if you can't remember everything that goes on, I highly recommend that you go through this and through this and through this. There is a video on the channel about all of this stuff, right? So I'm not going to spend ages on it. I'm going to just blast through it and make sure that It makes sense to everyone, all right? So, first of all, the value stored in the PC is copied to the MAR, right? The MAR tells us where in the memory store we are going to look, right? Unlook, guys. What does that mean? So, MAR is the address we are currently going to look up. Right, in the memory store at memory address 0 is this value LDA007. Right, what happens to that? It gets copied across the data bus and stored in the MDR. Like that. Okay. Once it has been copied across to the MDR, it is then stored in the CIR. It's copied from the MDR into the CIR. Okay, at that point, the program counter increments, and that is the end of the fetch. Okay, all of that stuff happens during the fetch. Yeah? Copy a PC to the MAR, look up the address in the memory store stored in the MAR, copy that information across the data bus and store it in the MDR. Yeah? Once you've done that, you copy the value from the MDR into the CIR. Once you've done that, increment the PC. Right? That's the end of the fetch. That's not the end of the whole cycle. Right? We now have in our CIR, we have this value LDA007. Right? The decode splits the instruction stored in the current instruction register into opcode and operand. Okay? The opcode is basically the bit that tells us what we're actually going to do. The operand is the bit that tells us the information that we need in order to do that. Right? In this instance, the opcode is LDA, right? And the operand is #007. You do not need to know what these different commands are. Right? You don't need to know that. You just need to know what happens during the fetch, during the decode, and during the execute. Okay? So after we have decoded it, we will have an opcode, which is the bit that tells us what we are going to do. And then we will have an operand, which is the bit that we're actually doing that thing with. Right? So, as I said, you don't need to know this. LDA means load data into the accumulator. #007 means we're going to load the actual value 007 into the accumulator. So once we've decoded, we execute, and now that we're executing it, we're doing the thing in there, so we're going to load that value into the accumulator. Boom. That's it. Okay? The trickiest part is remembering the what happens during the fetch. Alright? So let's go through the fetch again. We copy the value from the PC into the MAR. Yeah, without a hash, it means look up that location in memory, which is what I'm going to show you next. Okay, so our value in the MAR is now 1. That is the address that we are going to look up in the memory store. So we go across the address bus, we look up memory store location 1. It is currently got LDA011 in, so we're going to copy that across the data bus, store it in the MDR. Boom, there it is. We now copy the MDR from, we copy the value from the MDR into the CIR. And then finally, to complete the fetch, we increment the PC by 1. So the PC is now 2. That's the end of our second fetch. Okay? We now need to do the decode. So we look at what's in the CIR. We decode that. What is the opcode of the instruction in the CIR? What is the opcode of the instruction which is currently in the CIR? LDA is correct. Okay, it's another LDA instruction. And what is the operand? 011 is correct. Okay, so now we have done the decode, we've split that up into opcode and operand, we are ready to execute. Okay, be careful here, it is not #011, it is just 011, which means we are not going to load that actual address into memory. We are going to load we're not going to load that actual value into the accumulator. We are going to look up that address in memory and load whatever is stored in that address into the accumulator. Okay, so when we execute this, we copy the we're copying the operand into the memory address register. Okay, 011. We are then going to look up that location in the memory store. Currently at 011 is the value 10. That gets copied across here. Okay, so you can see here, because we have now obliterated what was stored in the MDR, that shows us why we need the CIR in there in the first place, so that we can actually still understand what instruction we're carrying out even while we're executing the instruction. Okay, now that we've copied that value across, we copy it into the accumulator. Okay, that's all there is to it. I'm not going to bother going through all of this again because, like I said, there's a video on it. You don't need to know how these different instructions work. You just need to know the steps involved in the fetch. You need to understand that the decode will split the instruction into opcode and operand, and then the execute will do whatever it needs to do. Okay? You don't need to know it in as much detail as this, but if you follow the video which is on the channel about systems architecture, that should get you all totally clued up. Okay, does that mostly satisfy those of you who needed to go over the fetch, decode, execute cycle? Good. Okay. Remember, if you're ever in any doubt, your best bet is to go through this process. Do a fetch. Do a fetch. Keep on fetching. Keep on decoding. Okay. Don't worry about how it executes. Just do a fetch. Do a decode. Do a fetch. Do a decode. Do a fetch. Do a decode. Okay. Good. Right. So we've done von Neumann. We've done system architecture. Boom. So system security was the next thing that you guys wanted to look at, right? System security. Anything particular about system security that you want me to go over? You wanted to go over some of the ciphers, if I remember. Okay, Joey, thanks for tuning in. Different attacks. So I'll tell you what I'm going to do. I'll bring up the spec. Here is the specification. We'll go down to the system security. So here's the stuff that you need to know about system security. Learners should have studied the following: forms of attack, threats posed to network in terms of malware, phishing, people as the weak point in secure systems, like social engineering, brute force attacks, denial of service attacks, data interception and theft, the concept of SQL injection, not the actual execution of the SQL injection, just the understanding that SQL injection is a thing and understanding what actually goes on without the specifics. Okay, poor network policy. You guys should know all about poor network policy. Identifying and preventing vulnerabilities, including penetration testing, network forensics, network policies, anti-malware software, firewalls, user access levels, passwords, and encryption. Okay, so out of those things, what would you like me to go over? While you do that, I am going to go and do a thing, and then I'll be back in like a couple of minutes. So you guys discuss this, and then I will look forward to seeing a whole bunch of answers. Yeah? A whole bunch of answers when I get back. I shall return shortly. Hey yo, I'm back, blood. What does system security want me to go over, innit? Let's have a look. What are we discussing? He is going to eat small people and the rest of it too, doing multiple blah 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 blah. I don't really get this bit of the course. Okay, right. Let's see what we can do to help you out here. Dun, 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 ba, bum, ba, bum, bum. Okay. Computer systems are generally pretty weak, and the reason they're pretty weak is because people use computer systems and people are weak. Okay? You can easily trick someone into giving you their information, and that's one of the things that you need to know about in terms of phishing attacks. Have I got something about phishing attacks in here? Somewhere. We'll get onto that, okay? Ways to protect computer systems from attack. You guys probably all have passwords for some various things that you do on your computer. How many of you use two-factor authentication for services and stuff? Good. If you're not using two-factor authentication, you should be, because it doesn't really matter how secure your passwords are. You can be tricked out of them pretty easy, and also if people get hold of your passwords, they publish them online and stuff like that. You're best off with two-factor authentication, because then if someone does find out your password, they will be able to access your stuff, but they won't actually be able to log in because they won't have your phone, because you will have that with you. I'm assuming, by the way, that you all know what two-factor authentication means, and I don't have to go over that. No password is uncrackable. No password is uncrackable. I could beat you with a wrench until you tell me your password. I'm not gonna, because I'm a nice guy. But I could. Yeah? It's not uncrackable. Right. Antivirus software protects your computer, because if someone sends you a virus, a lot of the time the viruses that get installed, or Trojans really that get installed, are going to install some software that phones home, so to speak, and sends bits of information to people. Okay? It will send things like your keystrokes that you type in. It might even detect when you're on certain websites, and it might record the keys that you press and then send that information across, and then someone will gain that information. Okay? If your machine is not infected by viruses, then you don't have to worry about viruses sending information across the internet. Right? Makes sense. You need to make sure that your antivirus is regularly updated, though, because new viruses are coming out all the time, and if your antivirus software is not up to date, then said viruses may get onto your computer. Okay? Boom. Next up, firewall. If someone is trying to hack into your system, they are going to be making a connection to your computer. Anytime you allow people onto your computer, they will access your computer through a port. When you access a website, usually the port number is 80. Okay, so they're coming on port 80. If you're using SSH, I think it's port 21, and so on and so forth. Okay, you can close these ports with your firewall. You can say, nope, nothing is allowed in through port number 80, in which case you won't be able to view most websites. You can also say, why 80 specifically? Because that's what it is. I mean, it's one of those numbers. Let's use port 80 for HTTP. That's generally how it works. I'm just pulling up a list of regularly used port numbers here. Yeah, you know why Aardwolf uses port 23, right? Because it uses Telnet. Telnet is port 23. What else you got here? You've got FTP uses port 20 and 21 apparently. SSH uses port 22. Telnet uses port 23. Email uses port 25, and so on and so forth. There's tons of different default ports, but you can change the port, right? Windows Defender has it covered. Yeah, I guess. I mean, the thing is, you can block data coming in, but you can also block data going out. Why do you think you might want to block data going out of your computer? Yeah, keyloggers, basically. That's stuff that I just mentioned with your viruses sending information out. Not just keyloggers, but also some websites that you visit might be able to access parts of your computer and then send it out. They're usually via the form of cookies. Remember when you go to a web page and it says, oh yeah, we use cookies, is that alright? Yeah, and you just say, yeah, okay, click. You ever thought about what kind of information might be getting sent out? You know, maybe you should. Maybe you should think about that information. When you sign up for a social media platform like Facebook, they are taking your information. They are sending that information out. You should probably think about it. Okay, I would recommend not using social media because they are harvesting your information and they are sending it out. And you're probably thinking, oh yeah, but adverts don't work on me. Yes, they do, because you don't know that they are adverts. Yeah? Whenever you buy something because you think that's cool, why is it cool? Because you see other people using it, right? Why do you see other people using it? Because a profile has been built about the things that you like, okay? And those stories about people using that thing that you like are targeted to you. Okay, you got to remember, harvesting data is not about targeted advertising, it's about controlling your behavior. So you really should pay attention to what you are clicking on. Okay, so yeah, firewalls. The thing to bear in mind with firewalls, they stop traffic coming in, which is obviously going to stop nasty hackers from accessing your computer. They also can stop traffic going out, which is going to prevent Trojans and stuff sending information out to the rest of the internet. Okay, okay. You need to know about penetration testing, right? Penetration testing is sometimes known as pen testing. What this is where you employ a company to try and hack into your system. They will find areas of weakness and they will hack those areas of weakness and they will say, this is how we got in and this is how you can fix it. Okay, now obviously pen testing needs to happen before something bad happens, because after something bad happens it's too late, right? So you need to make, if you want to test your system security, you need to get the penetration testing done before anything bad happens, right? Yeah, the people that do pen testing are sometimes known as white hat hackers. So if you're not aware of that, there are kind of three types of hackers, if you like. There's black hat, which are the bad guys. There's white hat, who are the good guys, and then there's grey hat, who are sort of like supposedly neutral. Yeah. So there's the thing. Yeah, they don't actually wear hats. It's just, you know, it's a turn of phrase. But the whole point is that you are paying someone to effectively test your security. It's kind of like if you just fitted a new lock to your house and you want to make sure that it's totally secure, you hire someone that's very good at breaking into houses and you say, can you try and break into my house? If they can't break into your house, you know the lock's secure. If they can break into your house, what they're going to do is they're going to say, this is how I got into your house. If you do this, I wouldn't have been able to get into it. Okay, that is basically what penetration testing is all about. I mean, you could probably wear a hat if you wanted to, but most of the time they don't. If you want to be a good hacker, you don't make out that you're actually a hacker. The worst hackers are the ones that brag about their exploits, because that's how you get found out. If you're a decent hacker, you go in, you do what you got to do, and no one ever knew you were there. Yeah, people don't become hackers for glory. If you're becoming a hacker for a glory, then you've chosen the wrong path. Yeah. And just following on from what I just said there, things to bear in mind, right? People are rubbish. People are easily tricked. For instance, people might believe that advertising doesn't work on them, when in fact they have been manipulated with fake adverts, or they have been fed a heightened amount of information related to a particular product or service without realizing that they have been served covert adverts. You can trick information out of people. Sign up for my survey. You might win a phone. Oh, cool. Okay, I'll sign up for that survey. I just need to fill out this information. Well, there you go. I've got your information now, right? What's your wrestling name? Your wrestling name. Your first name is the name of your family pet when you were growing up, and the second name is the name of the street that you grew up on. Both, by the way, are the sorts of security questions that banks will ask when you try to reset account details and stuff like that. Never ever fill out that kind of information. Never ever give that stuff away. Right? If you're gonna, make it up. Yeah. So don't ever give that information away. Just if someone says, "Oh yeah, here's a funny thing for you to do," no. And how many of you used that? Do you remember there was that app where you take a photo of yourself and it makes you old? How many of you used that? Just by show of hands, or just saying me in the chat. How many of you use that app to make you look old? Sensible people, because if you had done that, then people in Russia would have had your facial recognition data, and they will be able to profile you based on that information. Okay, but the thing is, it's not just those sorts of apps, right? Anytime you take a picture of yourself and upload it to the internet, you are giving away information about what you look like. Anytime you post a selfie on Instagram, that information is up, and it is against your name, and people will be able to identify you with it. Something to think about, isn't it? Okay. Now, the way to try and protect your computer systems, right, is to make sure that the people understand the sorts of attacks that might happen, right? At school, fairly recently, we did a test, and an email was sent out to all staff members saying, your email account is going to be closed. Click here to make sure that your email account does not get closed. Now, I wasn't aware of this, and so when I received the email, I immediately sent out an all-staff email saying, just be aware that there's some dodgy emails going around. Now, it turns out that it was just a test, okay, but some people didn't get my warning in time, and some people did click on the link, and if that was a genuine attack, there's potential that we could have lost some data. Okay, but these are some of the ways that you can ensure that your systems are secure. Okay, those people that did click the link, they then were provided with proper training, and when we reran the test, no one clicked the link. Okay, who would have thought that teaching people stuff would make things better? Crazy. So yeah, I'm just going to mention network policy. A network policy is a list of rules which everyone needs to abide by, and if you abide by those rules, in theory, the network will be secure. This is where things like blocking web pages is useful, because certain web pages are going to be slightly dodgy and they might harvest information. One of the reasons why we block social media at school is because it is constantly harvesting information. And it's a massive distraction. I mean, there's that, right? And you guys can't be trusted to just focus on your work. You know, I wish I could trust you to focus on your work, but you know, sorry. But you know, your kids. What can I say? I mean, I still get distracted by more interesting things on the internet sometimes, and it does take a lot of willpower to stay focused on what you want to do. So anyway, that's that. But network policy is obviously it's set up to make sure that bad things don't happen. If you don't need to access a certain type of website, just block it. There's no point. Okay, it's better to limit the amount of stuff that you can access than to deal with the aftermath of accessing a site that you shouldn't have accessed. We are humans with limited attention spans. Yeah, that's the point that I'm making, Alex. Humans are weak. Yeah, humans are the weakest link in any computer system. That's what I'm saying. Humans are weak, right? And young humans tend to be a bit weaker, or maybe just less cynical or less well trained than the people that have been doing this stuff for a long time now. I'm not saying that adults universally are more switched on. Most of the time they're not. Okay, but just throwing that out there. The school's firewall is so strong, half the websites you need are blocked. Yeah, so let's get this straight. That's not the firewall. That is the web filter. Two different things. Okay, the firewall blocks access on ports, right? The web filter specifically prevents certain websites from being accessed. They're two different things. Web filter, firewall, not the same thing. Okay. Yeah, I do know what you mean, Alex, but I'm pointing it out so that if there was a question where you needed to distinguish between a web filter and a firewall, you wouldn't get marked down. Do you see what I mean? Okay, George was an accident was his harmed in an accident was his fault. Okay, I don't know what that means. So you guys need to know a little bit about encryption as well. I don't really know what to tell you that I haven't already gone over fairly extensively, but encryption is basically where you scramble stuff to make it difficult for anyone except the intended recipient to read, and that's the crucial thing. It's not scrambling stuff so that no one can read it, because then that's useless. You might as well destroy the data. You want to scramble it so that only the intended recipient can read it. Okay, let's have a look. What have I got here? I've got some stuff about malware by the looks of things. Let's have a look at the malware. What is malware? Oh, man-in-the-middle attacks. You guys want to know about man-in-the-middle attacks? Or how to calculate hex. I've already gone over how to calculate hex, so you will have to, once the video's finished, if you rewind, you should be able to find that bit, because I don't have time to go over it again, because it's already 8:10 and I'm going to be finishing in a minute. But let's go through some of this stuff. Malware. What is malware? It's bad software. It's malicious software. It's software intended to harm stuff. But we've gone over that stuff, right? You need to know about these things: data interception, denial of service, and SQL injection. You also need to know about brute force attacks. Data interception. If you fake a node on a network, you can intercept traffic. You can change the traffic before it reaches the intended recipient. Okay, which means you could potentially, even if they are encrypting their data, what you could do is you could say to them, "Oh, you know what? I didn't receive that information properly. Can you re-encrypt it with this key?" They then re-encrypt it with that key. You can then read their information. You can change that information before you send it on to the other person. Okay, a man-in-the-middle attack is where data is intercepted and either read or changed on the way to its intended recipient. How to protect against man-in-the-middle attacks? I mean, encryption kind of works, but there are ways around it. The best way of protecting against man-in-the-middle attack is by using asymmetric encryption and data signatures. okay, which tie together. A data signature is basically you use an encryption cipher, an asymmetric encryption cipher, which digitally signs the information that you send, and it uses a private key which is stored on your machine and only you have access to it, and it signs it with that digital key, and then anyone else, if they try and sign it, if they intercept that information, they change it, when they sign it, it will not work because they don't have your private key. And then when the intended recipient receives that information, it will say, you know what, this is not valid. This is not a legit message. Okay. What on earth are you guys talking about in terms of cardiovascular disease? It's got nothing to do with what we're doing here. Oh look, I've got a little bit of look. There's a digital signature. Yay! Denial of service attacks. That's where everybody tries to access one thing at one time, and it causes a server overload, and it basically breaks the server because it can't cope with all of the pressure. Now, a standard denial of service attack, that is where a single node on a network is spamming the server. A distributed denial of service attack is where multiple zombie systems on the network will all target the server at once, okay, and overload the system. Now, the way to protect against this sort of stuff is using flood defenses. Your server, you can set up your server so that if it's receiving a high volume of requests from a single place, it will say, no, not having it. You gotta wait. Okay. The same sort of thing happens if it's receiving a bunch of similar requests at the same time from multiple different places. It can say, you know what, I'm just stop all of those requests. Okay. So yeah, I've gone over this. You can sort of like read into that. SQL injection. You don't need to know exactly how to perform a SQL injection attack. You just need to know the concept behind SQL injection, and that's where you inject some SQL code, so something that is used to access databases. This works on database driven websites like, for instance, WordPress and stuff like that. You inject some code into a web form. So for instance, there might be a form where it's like, hey, type in your username, and instead of just typing in your normal username, you type in a string terminator and then a whole bunch of SQL, and then what happens is when that request reaches the web server, it sees the stuff that you've typed in, and then it sees the SQL and it executes the SQL as if it's a command, which allows you access to the database. Here's the example from XKCD. So you can see here what the son has typed in here is Robert apostrophe close brackets semicolon drop table students blah 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 blah. Now, just to demonstrate what that's going to look like, if you have a field which is taking in some text value, it's going to start off. The actual SQL request might be something like select star from users where user equals whatever they've typed in. If I type in Smith like that, that's what it might look like. Now, if we take that same string there, right, but we replace it with what's been typed in the box there, let's just have a look at how that gets changed. Right? Instead of typing in Smith, what have we got here? We've got Robert, close bracket there. I mean, this might generate an error, and then drop table students. So you can see what it actually receives is it receives this full instruction here, and then it will go on to execute the next instruction. That's basically what any kind of injection attack does. It fools the system into thinking, right, that instruction that you've just done, that's finished. By the way, here's another one. Okay. So there you go. And then finally, brute force attacks. We looked at this fairly in depth. That's basically where you exhaustively try every single combination that a password could possibly be over and over again until you get the right thing. There's not really any way to protect against brute force attacks other than, can someone suggest a way to protect against brute force attacks? Complex passwords will not protect against brute force attacks. Given enough time, they will be cracked. Limiting the number of attempts will delay a brute force attack. It won't stop it. Really long and complex passwords, again, that's just going to delay it. It's not going to stop it. Now, you can delay it for a ridiculously long amount of time, but there's a better way. I've already mentioned it once. Yeah, two-factor authentication. That's what we're going for here. Okay, you can brute force a password, but even if you get that password, if they've got a two-factor authentication set up, doesn't matter, you know. And what's going to happen is they'll say, oh, someone tried to access your account, but they couldn't because the two-factor authentication. Highly recommended that you change your password. Okay. Dun, 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 dun. That's basically it for this. Who was it that wanted me to go over Insertion Sort? I'm pretty sure I've got a video about that, and let me just have a quick look here. I'll very, very brief because I'm aware of the time. We've been going for a long time now. Let me just quickly find this Insertion Sort. Boom. There we go. Dun, 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 dun. The insertion sort is ridiculously simple. You start off with a list of numbers. Here's my list of numbers, right? The first number in the list is the sorted list. Okay, anything to the left of this point here is sorted. Anything to the right is unsorted. I have coloured the sorted list green, and I have coloured the unsorted list cyan here. Okay, what you do is you look at the next number in the unsorted list, and you just put it into the right position of where it should go in the sorted list. So I've got the number 10 here. 10 goes before 23, so our sorted list becomes 10, 23, and then all of the rest of the unsorted list is exactly the same as it ever was. The next number that we're looking at is 2. So where does 2 go? Well, 2 goes before 10, so there's our number in the sorted list there. Everything else remains exactly the same. We're looking at the next item. It's 4. Where does 4 go? We track backwards here. It goes before 23, it goes before 10. It doesn't go before 2, so the 4 goes in there. Boom. Okay, there's our sorted list. Now we look at 8. Where does the 8 go? The 8 goes before the 23, it goes before the 10. It doesn't go before the 4, so it slots in there. There's our sorted list. There's only one number left. We don't need to work out where that goes in this example because it is already where it needs to be. That's it. The insertion sort is really super simple. It's just a case of looking at the next number in the unsorted list, finding out where it goes in the sorted list, and following down. That's it. Okay? Boom. Which means I just wanted to go over some exam technique with you before I sign off. I mean, how long have we been going for now? We've been going for a while. Does it say how long I've been going for? 2 2 and a bit hours by the looks of things. Average watch time 26 minutes. Well, that's kind of cool, isn't it? Right, okay, so exam technique. What advice can I give you? First of all, read through the entire paper before you start answering any questions. Okay, make a note of which questions you think are going to be the easiest ones to answer and answer those ones first. If you get stuck on a question, don't panic, and also don't spend ages on it. Right? Look at how many marks each question is worth. You should pace yourself. You have 90 minutes and there are 80 marks. That gives you approximately 1 minute per mark plus 10 minutes checking time at the end. Right? If you've got a 1 mark question and you are spending 5 minutes racking your brain to try and work out what the answer is, it's not worth it. Skip it, move on. Okay? The other thing as well, don't leave a question blank, right? Now, I know I've just said skip it and move on, right? But here's the thing. When you get to the end of the paper, you've answered all the questions you can. Go back, look at those questions that you left out. Have another crack at them, and if you still can't answer them, just write down the first thing that comes into your head. If you write nothing down, you are guaranteed to get 0. If you write something down, there's some small slim chance that it might actually give you an answer. Okay? When you are writing essay questions, make sure that you write in complete sentences. The way that the exam board, a lot of the time they don't actually write the quality of your written English will be assessed in the answer to this question. They will say on the very front page, questions marked with an asterisk will judge the quality of your written English. So just watch out for that asterisk wherever it might appear. And yes, there is one in there. Okay, so just be aware. What is there on the test that we haven't looked at all today? Just so I can go through it. Well, anything that we haven't covered, which is on the spec. You know, I'm not telling you what's on the test. I'm telling you what could be on the test, and it's literally anything that's on the spec. So if we just have a quick look at that, we have covered systems architecture. We haven't covered memory, we haven't covered storage, we haven't covered wired and wireless networks. We've covered network topologies, protocols and layers, we've covered system security, we haven't covered system software, we haven't covered ethical, legal, cultural and environmental concerns. We've covered some amount of algorithms. We haven't really covered much programming techniques. We briefly touched on producing robust programs. We've covered some computational logic. We have covered data representation. That's your binary conversions and stuff like that. Okay. So all of that stuff could potentially arrive on the paper. I'm not telling you what's on there. I'm not telling you what's not on there, because in the real exam you don't get to know. That's the way it is. And remember, I have been banging on for ages that you should be revising, like say 15 minutes a night every night anyway. Okay. So again, I'll just echo what I said right at the start. Don't panic. If you fluff it up, it's not the end of the world. Okay. Obviously, go in there, give it your best shot. But it really isn't. I mean, even your actual GCSEs are not the most important things in the universe. Everyone bangs on about it being, oh, it's the most important. No, it's not. Okay. There's no point getting stressed out about something like this. It is not the end of the world if you mess these things up. Obviously, it's better if you don't mess them up, but you know, it's not like your life is instantly over. There's more important things to life, so don't stress about it. Okay, if you do have any concerns, you can come and speak to me tomorrow. I'll be around most of the day, and I'll be around, I think I'm around after school as well if I don't have anything on. Okay, so what are the grade boundaries? I do not know. There'll be whatever OCR published grade boundaries are. Okay, it's the same ones that I've been using, unless they've changed suddenly. They'll be the same ones that I've been using for the end unit tests. Okay, but I wouldn't worry about it. Just do your best. Doesn't matter. There's no point knowing the grade boundaries, because then you'll be like, oh, you know, I reckon I got this grade. It doesn't matter. Do the test, and then it's done. Focus on the next test that you've got coming up. Okay. But yeah, I mean, ultimately it doesn't matter, like whether it's a 9 or an 8 or you know, don't worry about it, basically. Just answer the questions as best you can. That's it. Oh, it's the last one, in which case you can do the thing, forget about it, and have a come back and then do your programming project. Sorted. Right. It is currently 8:26. I have been banging on about all manner of computer science related nonsense for nearly 2.5 hours. That is a substantial amount of my weekend. I hope you guys appreciate this. Subscribe to my Patreon or something like that. You don't even need computer science to take at A level. Yeah, that's correct. But if you do computer science GCSE and you don't get a decent grade, I will not let you on the A level course. There you go, because you've proven to me that if you can't even do GCSE, there you go. Okay, show us your dinosaurs. These ones, you mean? Dun, 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 dun. What have we got? Oh, look, it's a glowing Stegosaurus. Yay, Stegosaurus. Dun, 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 dun. Do I have any more dinosaurs? I got a dragon. It's not a dinosaur, really. It's a dragon. But... There you go. Cool. That's that. Right. Thank you very much for your time, everybody. I'll see you all tomorrow. Get a decent night's sleep and read more books. Okay, if I could give you one piece of advice for every single thing in life, it would be read more books. And anyone that thinks that is a silly idea is a fool unto themselves. Read more books. If you want recommendations on books to read, I can give you tons of recommendations on books to read. If you want some free books, I could probably sort you out some free books, but you guys need to read more. Everyone does. All right. Thank you very much, everybody. Go and have a wonderful night. Do something good. Dun dun. Dun 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 dun. Oh, tell you what though. It's £9,500. How about? Yeah. How about this music? That's it, I'm done. Thank you very much. Goodbye, everybody. See you later.